Okay, we're in 11.6 of Barnett, and we're looking at related rates. That's the topic of this section. So our goals for this section, the objective is to be able to solve related problems and applications, and specifically we'll look at business applications. So we'll do an example in this video as well. Well, related rate problems usually involve three variables. In our course, they will at least. They involve an independent variable, which we often denote by t, as it represents time, and two dependent variables. Our goal is to find a formula for the rate of change of one of the independent variables in terms of the rate of change of the other one. That's what we mean by the related rate problem. You're relating one rate of change to another rate of change. So these problems, since we have rates of change, are solved by using a relationship between the variables, then differentiating that relationship and solving for the term that we're looking for. So the best way to do this is to look at a few examples here. So here's an example. A weather balloon is rising vertically at a rate. The word rate means that we have some sort of a derivative here, 5 meters per second. So this tells us how one variable, the vertical height in this case, the vertical rise, is changing with respect to time. It says an observer is standing on the ground 300 meters from the point where the balloon was released. At what rate is the distance between the observer and the balloon changing when the balloon is 400 meters high? So getting a picture going is an important part of the process here. So here's a picture. We have our balloon in purple, like you see here, and it's rising vertically up. And the independent variable is time t. So what are the quantities that change with respect to that variable t as mentioned in the problem? Well, the vertical height will change, and the distance between the balloon and the observer that we have here would also change. So we're going to use variables to denote those. We're going to use x to denote the distance from the observer to the balloon, and y to simply be the height of the balloon. And remember, this number here, 300 meters, stays fixed. This is the distance between the base where the balloon was and the observer. Keeping all of that in mind, we solve the problem knowing that dy dt is given, right? It's 5 meters per second. In other words, the balloon is rising up at a rate of 5 meters per second. Okay? What we're looking for is dx dt. How is the distance between the balloon and the observer changing? Okay? So we need a relationship between x and t so that we could derive that relationship to get a relationship between these two rates, dx dt and dy dt. Well, notice this forms a right triangle. So we could use the Pythagorean theorem, which says the sum of the legs squared is the hypotenuse squared. And in this case, that means 300 squared plus y squared is x squared. Differentiate both sides of this equation with respect to t. The derivative of any constant is 0. The derivative of y squared is 2y dy dt. So we have y squared. When you take the derivative, remember y is a function of t. Therefore, when you take the derivative with respect to t, this is 2y dy dt. That's what we get there. Likewise, x is a function of t because as time passes, this distance here changes. Therefore, the derivative of x squared is 2x dx dt. We were looking for dx dt, so we isolate that by itself on one side of the equation. In other words, simply divide both sides by 2x here. And that's how we obtain y over x dy dt for dx dt. Okay, we could simplify this a little. And why? Because we know that we need the values for x, y, and dy dt in order to solve the problem, right? This is a general relationship. This is true in general for any t, and for any x, and for any y. But we know that our y is 400, our dy dt is 5. We're looking for our x. We're looking for the distance between the balloon and the observer. How could we find this? We could find this using the Pythagorean theorem. Knowing that x squared is 300 squared plus y squared allows us to conclude x is the square root of the right-hand side. And we know that y is 400. That's what they asked us in the question. Find the rate when y was 400. That happens to give us 500. Okay, we know dy dt is 5, so just go ahead and plug everything into this expression. Y over x becomes 400 over 500, and you're multiplying that by 5, which is dy dt. That's how we obtain 4 meters per second. So in general, when you're solving related rate problems, these 6 steps are helpful to remember. Make a sketch if possible. Identify all variables, including the ones that are given and the ones you're looking for. Express all rates as derivatives. Find an equation connecting the variables. Differentiate the equation and solve for the derivative that you are looking for. Right? Related rates. One derivative is given in terms of another. Here's an example from geometry that's sort of applicable to the real world. Right? We have a rock that's thrown into a still pond and it causes a circular ripple. Everybody has seen that ripple effect when you throw a stone into a little pond or a river or a lake or something. So if the radius of the ripple is increasing at 2 feet per second, how fast is the area changing when the radius is 10 feet? Once again, we're looking at a particular situation when the radius is 10 feet. So we have a rate given to us, 2 feet per second. That's the rate at which the ripple is increasing. And we have that we're looking for the area when the radius is 10 feet. And they remind you the area of a circle is pi r squared. Here's a picture, right? So we throw the rock or the little stone here into the still pond. The radius of the circles really, right, that occur, the circular waves I was going to say, increases. So let r be that radius, let a be the area, dr dt in this case, the rate at which the ripple is increasing is 2 feet per second. Okay? And r itself is equal to 10. That's what's given. We're looking for dA dt. How is the area of the circle changing? Well, all we have to do is start with the given formula that relates these variables, a and r, and differentiate with respect to t. On the left-hand side, we'll get dA dt. On the right-hand side, we get 2 pi r dr dt. Notice, r here is a function of time. The radius increases as a function of time. It depends on how much time has passed since you've thrown the rock. Okay, so now substitute the appropriate values that you have into this formula, and you obtain 40 pi. So dA dt must be 40 pi. Finally, let's take a look at an example from business. Suppose that for a company manufacturing transistor radios, the cost and revenue equations are given by the following equations for C and R here, respectively. Where the production output in 1 week is X radios. If production is increasing at the rate of 500 radios per week, there is a rate, 500 radios per week. When production is 2,000 radios, the other given quantity, find the rate of increase in cost and in revenue. So follow these 6 steps that we came up with. Okay, with the business problems, there's really no drawing to be done, but let's identify what we know and what we're looking for. So it says these are really 2 related rates problems, one involving Cx and T, the other involving Rx and T, part B. This would be for part B. This one is for part A. Okay, so in part A, we know that C is equal to 5,000 plus 2x. We differentiate the equation with respect to time. dc dt is twice dx dt. That gives us 1,000. That means the cost is increasing at a rate of $1,000 per week. Likewise, to figure out what's happening with the revenue, at what rate it's increasing, all you have to do is differentiate dr dt and find out. Well, you know that dx dt is 500, right? That was given in our problem. If we go back here, it says that the production is increasing at a rate of 500 radios per week. That's where the dx dt equals to 500 comes from. Plug that in, and you get 3,000. So revenue is increasing at a rate of $3,000 per week. It's as simple as that.